has been driving you crazy, or if you're finally admitting you're lazy, and your test grades have been dropping, it's time to get your arrows popping. Hello, it's Mr. Witt and Fort Bend Tutoring, and today we have a good lesson for you today. Oh, yes, we do. We'll be talking about tests for symmetry. That's right. Tests for symmetry, ladies and gentlemen. That's exactly what we'll be focused on today. And we have some people in the chat already. We got Sandra in the chat. We got Obina in the chat. We got Claire in the house. We have Smarty Pants, aka Karina, is in the house. And we are going to go over some problems today. Yes, we are. I just would like for you to subscribe to Fort Bend Tutoring. That's right. Go ahead and click on that subscribe button. Oh, yeah. There you go. Darian Jones is in the house as well. Just talking about what's up, Mr. Witt. What's going on, Darian? That's right. And I want you guys to make sure that you're sharing the stream. Go ahead and do that. Oh, yeah. Go ahead and share the stream. Also, go ahead and post those links on your social medias, inviting your friends and your family and the people that you hate to the party. That's right. Let's have everybody in the house to share with the knowledge and wisdom that Fort Bend Tutoring is offering today, ladies and gentlemen. That's right. That's what we got going on. Let's go ahead and get the chat on the screen real quick. Let everybody know that I'm not just talking to myself right now. There we go. So there you go. You got the chat in the house with Smarty Pants, who is excited today. That's right. Karina is in the house and she is live and ready to get things started today. So guys, I just wanted to share with you the problems. Let's just go ahead and cut to the chase real quick. Let me go ahead and show you the problems that we'll be looking at today. So some of these problems are functions. Some of them are not. That's right. So we'll be looking at different types of problems today. Claire is chiming in the Philippines at 1:08 in the morning. What's going on there, Claire? Thank you so much for spending time with me in the wee hours of the morning. Appreciate that. That is a serious commitment to FBT. That's right. Let me go ahead and change up the focus a little bit here on the camera just to make sure that it will be in proper view for everybody. Okay, I think that's a little better. All right, I think that's a little better. Okay, I think that I can deal with that. There you go. I'd rather the top of the screen. There you go. Be focused than the bottom of the screen. All right, we're gonna get this straightened out. We're gonna get this straightened out for you guys. So just to let you guys know, these are the 15 problems that I have prepared for you. There you go. We'll be testing for symmetry in each of these equations. Notice that I have a trigonometric equation right here for number 15. There you go. So therefore, we'll be hitting on classes like college algebra, pre-calculus, as well as trigonometry in this lesson here. I like to sprinkle a little bit of the concept across various courses just to help you guys and also to let you guys in the near future, especially if you're transitioning from one course to the next, how you can apply these concepts that we go over in other classes. All right. So that's another important aspect of what we bring to you as far as the lessons, the sessions, the lectures, the videos that we put out. There you go. So this is going to let you guys know which problems we'll be looking at today. And let's go ahead and dig in with the rules for testing for symmetry. For instance, if you are testing for symmetry and you want to find out if a graph, if a function, if a relation is symmetric about the y-axis, then if for every point on that graph, you are just going to change the sign on the x values. See, if you take your x value and you go ahead and change the sign on that x value only and then simplify, and if you end up with the original equation, then you are dealing with a function, a graph, a relation that is symmetric about the y-axis. And as you see here, it says that if xy is a point on the graph and the opposite of x and y is also a point on the graph, the portion of the graph to the left of the y-axis is a mirror image of the portion to the right of the y-axis. In other words, the y-axis provides a mirror image to the left and right of that y-axis. That is when you are dealing with y-symmetry. That's right, y-axis symmetry. Yeah, that's what we got going on there. I don't like this little dot. This little stray dot right there, it had to go. I had to get rid of it. Next up, symmetry about the x-axis. What are we looking for here? We're trying to say that if you have a point on the graph and then you just change the sign on the y value and simplify and it's the exact same equation as the original one, then you have symmetry about the x-axis. Yeah. So they're saying that the x-axis will provide a mirror image to the top and bottom portion of the graph. Right. So not only are we going to be looking at graphs to determine whether we have y-axis symmetry, x-axis symmetry, we'll also be looking at just the equation itself and using algebra to simplify this to see if we can end up identifying the type of symmetry that the graph may have. What's going on, Mike? Good to see you. Mike Jackson is in the house. That's right. And I appreciate you guys. I really do. Spending time with me today. Absolutely. I appreciate your patronage on the YouTube channel. I appreciate you guys sharing the fact that we have these videos available to your classmates and to your teachers. And if you're a teacher, I appreciate you guys sharing with your classes as well. That's right. And your coworkers. It's all good. Let's spread the love. Let's move on. What about symmetry about the origin? You see what I'm saying? If you have a point, it's an ordered pair. It's x and y. If that's on the graph and the opposite of x and the opposite of y is also a point on the graph is unchanged by a rotation of 180 degrees about the origin. In other words, you can just turn. You could just go ahead and turn by 180 degrees in either direction. The graph, it will be identical to the original graph. If you replace the x value with a negative x, the y value with a negative y, and then simplify, you'll get the original equation. This confirms that you have symmetry about the origin. There you go. See, these are just all the rules. We're just covering all the rules right now. But of course, the fun stuff involves us actually doing a problem. And here we have problem number 1. And notice that we have the graph already here. We have the graph already here. We already have the graph. It's right there. And the equation for this graph, by the way, I went ahead and threw that in. It's going to be the equation y equals x squared plus 4. So we have a quadratic equation for problem number 1. The shape is a parabola. And our question is whether or not this graph is symmetric about the y-axis, the x-axis, or about the origin. Well, let's take a look at this. If the y-axis creates a mirror image for the left portion and the right portion of the graph, then we have y-axis symmetry. However, if the x-axis provides a mirror image, then you are dealing with an x-axis symmetry. If, for instance, the upper portion and lower portion is a mirror image of each other, and then if you can take the graph and turn it 180 degrees and it doesn't affect the shape of the graph, then you are dealing with symmetry about the origin. And only one of these tests will pass. And which one is that going to be? Which of these equations, which of these tests will pass here? Do you know? Well, it's the y-axis. That's right. See, the y-axis provides a mirror image. There you go. The left and the right portions. In other words, it's split down the middle because of the y-axis. There you go. So this symmetry here is about the y-axis. And how am I going to write this here? So this is symmetric about the y-axis. It has y-axis symmetry. That's what we're dealing with. The y-axis only. That's right. And note that you can have several symmetries occur at once. That's exactly what you can have. So Smarty Pants is absolutely correct when she says that it's y-axis only. Obina is already chiming in. He says that, yeah, I was about to say that, but Karina beat you to the punch, Obina. Don't hate now. Let's not be a hater. So that's why we're going to go ahead and put our result here in a red box. Just like that, ladies and gentlemen. So we are testing for symmetry. So the first thing we're going to do is we're going to identify symmetry based on the graph, and then we're going to dig a little deeper. Oh, yes. Let's dig a little deep. And we'll dig a little deeper here, and we'll figure out algebraically whether or not we can identify whether we have x-axis symmetry, y-axis symmetry, or symmetry about the origin. There you go. So Smarty Pants asks, so y-axis and x-axis symmetry can occur? Yes, at the same time it can. Absolutely. And then Obina says, yeah, but it's not every function in that case. That's correct. So you have to understand that, first of all, for a relation to be a function, it has to be able to pass the vertical line test. So in a lot of ways, if a graph has x-axis symmetry, it's probably not a function. Okay, because if that is a mirror image, that means that you are duplicating one of the values that will have the same x value, and you can't have that to have a function. So that's why I said at the beginning that we'll be looking at some relations, meaning that they are not necessarily functions, as well as functions, okay, and various graphs, and seeing whether or not these are going to have symmetry about the x-axis, y-axis, and origin. In other words, I came fully prepared for you guys today. That is correct. Let's look at the next problem here. Problem number two. Problem number two, guys, because look at what we have right here. Is this a function? No, it's not a function. It's not a function, and you should know this just by looking at it. Even though we're dealing with a parabola right here, it's a horizontal parabola, and it will fail any vertical line test because it will hit the graph more than once. There you go. So the only time a vertical line will hit this graph in one place is at the vertex right here. That's the only place, but it has to be that case, and it can't hit. A vertical line can't hit this graph more than once throughout the graph, and it definitely will hit it twice here, or even there. You know what I'm saying? So there's only one vertical line that'll hit this once, but the rest of them will hit them twice. Will hit the graph twice. Therefore, this is not a function. It's a relation. And we can see that visually, identifying that this is a mirror image across about the x-axis. What do you think? See, the upper portion, if you flip that over, it's going to be identical to the bottom portion. Okay, there you go. So that means that we are dealing with symmetry about the x-axis. The x-axis provides a mirror image. Okay. That the upper portion, the lower portion, they're identical when you flip it over, right? So therefore, we are dealing with x-axis symmetry. That's exactly what we're dealing with. And once again, we're just going to identify these at the beginning just based on the graph. Don't worry, the algebra is coming. Oh, yes, it is. So here I wanted to show you that if they provide you a graph, you can visually identify whether or not you have a relation that has x-axis symmetry just to see if it's going to split this graph down the middle here. If the x-axis splits your graph down the middle, if you have a mirror image on either side of the x-axis, you are dealing with x-axis symmetry. Oh, yes, you are. There you go. There you go. That's problem number two. And we put a black box around our answer that time. There you go. That's what happened. We're moving on. I have 15 problems. What you gonna do? We have problem number three. That's right, Sandra. We have problem number three. And we have x squared plus y squared equals 4. And we have treasure ghost in the house. What's going on, TG? How's it going there, treasure ghost? How you doing? I'm gonna show you a little love right here. Go ahead and show you a little love. Let everybody know that I'm not speaking to a ghost. I'm talking to Treasure Ghost. There you go. Just saying. We have a circle, guys. I know my circle looks messed up. I can't help it. This is the best I could do here. Okay? So, if this graph, if this relation, because it's not a function, it'll fail the vertical line test here. If this relation is symmetric about the x-axis, that means that the x-axis is going to provide a split down the middle, that either side, the left and right portions of this graph would be mirror images of each other, and they are. Obina says that this graph is going to be symmetric about the x-axis, the y-axis, and the origin. We shall see. And, oh my goodness, BGS Idmore provides another donation. Says, keep teaching the babies. I'm doing what I can, BGS, and I can keep doing it much more with your assistance. We have a super chat in the house. Let's go ahead and give BGS Idmore some love in the house, guys. Appreciate that, BGS, immortalized in FBT's videos with your smart super chat donation. I appreciate that so much there. That is the bomb, sir. Thank you so much. I appreciate your donation. And also, guys, you can use that $ at the bottom of your super chat there if you wanted to donate to Forbidden Tutoring. It helps us in all of our endeavors. Also, you can find a donation link in the description box if you choose to donate to Forbidden Tutoring. Note that all of the funds that you donate will go towards our free math tutorials and the free services that we provide to the world, ladies and gentlemen. So what we're doing here, Treasure Ghost, is we're identifying whether or not we have x-axis symmetry, y-axis symmetry, or symmetry about the origin. That's what this is focusing on. So these are tests for symmetry that we'll be focusing on in this video here. That's what we're doing here, Treasure Ghost. Good stuff. And once again, BGS Idmore is in the house with the donation. Thank you so much. Let's continue. So we've already identified that the circle here has x-axis symmetry, that the x-axis is a mirror image to the left and right portions. However, we can also show that the x-axis also provides a mirror image to the upper and lower portions of this graph here. Karina asks, what grade will we learn this in? Well, most likely you'll learn this in Algebra 2, most likely, and definitely in geometry. Geometry discusses symmetry as well, okay? So as early as 10th grade here in the U.S. is probably when you'll be introduced to symmetry. I doubt that they'll cover it in Algebra 1. However, geometry, that's 10th grade. Algebra 2, that's 11th grade. Pre-calculus, that's 12th grade for most people. And as well as your calculus courses and college algebra classes, obviously, will definitely deal with symmetry. So that's when you can look forward to that. But if you're in an advanced class, Karina, you can get it as early as 7th grade. Absolutely. So Karina is asking, right, I'm going to 7th grade next year. I understand that. But depending on your class, if you're in a GT class, an AP class, pre-AP class, you can get this as early as 7th grade, 8th grade, and 9th grade. So it doesn't have to mean that, and I'm just talking in generalities here, okay? So it depends on what your academic level is as to how soon you can see this. But you can get it today with me, Mr. Witt, and Forbidden Tutoring. How about that, Karina? Okay, so here's the deal. We already identified that this graph has x-axis symmetry. That this graph has y-axis symmetry. Absolutely. Now, if we were to rotate this graph 180 degrees, would it change any? Would this change if we rotated this graph 180 degrees? In other words, we just flipped it around. Would that happen? Would it be different? Absolutely not. It'll be the exact same graph, guys. The exact same graph. And that is why Obina is correct. This has x-axis symmetry. This graph has y-axis symmetry. This graph has symmetry about the origin. So it has all three tests for symmetry passed. Oh yeah. Let's go ahead and put this answer in a red box. So this is a relation, guys. It's not a function, but this is a relation where we're able to show that the graph itself passes all three symmetric tests, that test for symmetry. It passed all three. It is symmetric with the x-axis, the y-axis, and if you flip it 180 degrees, if you rotate it 180 degrees, it will be the exact same graph, therefore proving it is symmetric about the origin. Amen, amen. That's right, Obina. Obina says if it's a circle, it's symmetric about across all areas. But notice that would only be the case, Obina, if it's centered at the origin. Okay, let's say, for instance, let's go ahead and create another circle here. Let's say that I have a circle that is based right here. Okay, what if I have a circle right here? Would this circle, would it pass all three tests for symmetry? Would it? For instance, does it pass the y-axis symmetric test? No, it doesn't. So this is not going to be symmetrical about the y-axis. What about for the origin? Okay. Well, if I flip this 180 degrees, this circle would be over here. Okay. Does that pass it? No, it does not pass the test about the origin. However, it still passes the x-axis symmetry test because the upper portion and the lower portion are mirror images to each other. So in a situation where your circle is not based at the origin itself, then it doesn't pass all three tests. But this particular one in orange here, we can definitely confirm that it still passes the x-axis test for symmetry. Okay, so that's why it's important to understand the rules. Definitely. So that's correct, Karina. Only if it's based at the origin will the circle pass all three. So depending on if your circle is based somewhere else in the graph, it may or may not pass the additional test there. Okay, so that's why you have to look at each graph, each equation as an individual test, as an individual experiment to find out whether or not it is symmetric, okay, in respects to the y-axis, x-axis, and, of course, the origin. Let's move on, guys. You guys are asking great questions. That is right. Let's check out problem number 4. We have a rational equation. That's exactly what we're looking at. We have the equation y equals negative 1 over x, okay, and here is its respective graph. So once again, in problem number 4, we're looking to see if by looking at the graph, we can identify what type of symmetry we have with the graph. Remember that when you're dealing with the y-axis symmetry, the left and right portions need to be mirror images of each other. For the x-axis symmetry, the upper and lower portions need to be mirror images of each other. Obina says, I think this one is symmetric at the origin, and Obina is correct. That is correct. So because if we were to rotate this 180 degrees, it would end up right back in the spots that it would be in, and definitely would only pass symmetry about the origin. Sandra, good answer on that one, Sandra. Good answer. So this one is symmetric about the origin only. Okay, it doesn't pass the test for x-axis symmetry, and it doesn't pass the test for y-axis. Smarty Pants says half circles combined. All right. Oh, I see what you're saying. It's like 2 half circles there. Not really half circles though. Yeah, Treasure Ghost is correct. Not necessarily half circles. I can see what you're looking at though, Karina. But yeah, they're not necessarily half circles there. Good stuff. But we are moving on. Yeah, we are, because once again, we've confirmed that this graph, because of the 180 degree rotation being identical to the original graph, we confirmed that this is symmetric about the origin. It does not pass the test for symmetry about the x-axis, nor does it pass the test for symmetry about the y-axis, but we do have the origin taken care of. And don't worry about that, Karina. It's all good. We're here to learn stuff, all right? Like you said, you already said that you have not seen this before, so we're just ironing it out for you. But guess what, Karina? When you move on to 7th grade and beyond, you will already be aware of this concept, all right? Even if it's just a refresher at that point. So it's good that you're getting this exposure. Allow me to show you some things that you'll be using in the near future, and you'll be better for it. The fact that you're not wasting your time doing things that are not productive right now, that you're engaging academically right now during this time of the year is amazing to me, okay? It's something that I didn't do. So you're getting a leg up on me right now, Karina, and I'm proud of you. All right, so let's go ahead and move on, guys. We have problem number 5. And notice we do not have the advantage of looking at a graph from this point on, guys. We will be solving for symmetry algebraically. That's right. For instance, if you're going to test for y-axis symmetry, this is what you'll have to do. If you are to plug in negative x for all the x's and then simplify, then we're going to be able to confirm whether or not this is going to be symmetric about the y-axis. So if we plug in negative x for x and simplify this, we know that this negative x, this base of negative x squared, means negative x times negative x, which is x squared. So because our result simplified is equivalent to the original equation, this confirms that this graph, this equation, is definitely symmetric about the y-axis. Okay? And then let's go ahead and see about the x-axis symmetry. For the x-axis symmetry, the test for that is that you replace the y value with negative y and simplify this. So if, for instance, if I were to simplify this, aka try to solve this so that it's in a similar form to our original equation, I would divide both sides by negative 1. Dividing by negative 1, you'll end up with y equals to negative x squared. Well, is y equals negative x squared identical to our original equation? It's not. It is definitely not. Turtles unite. What are y'all talking about with these turtles? So here's the deal. With the x-axis symmetry, guys, we have y equals to negative x squared. This does not match our original equation. So therefore, this is not symmetric about the x-axis. Now to test for your symmetry about the origin. Testing for symmetry about the origin, if I can get my words right. We would be replacing every x with negative x. We would be replacing every y with negative y. So we have negative y equals to a negative x raised to the second power. You would then simplify this. Okay, simplifying this, you'll have negative y equals x squared. Then from here, we would divide both sides by negative 1, isolating that variable y. And you end up with y equals to negative x squared. Well, with y equals negative x squared, guys, once again, this does not, all right, this does not match our original equation. All right, so that means that once again that we only have y-axis symmetry. This doesn't work. This doesn't work. There we go. So we got checks and X's going on here. All right. Done and done. You guys in the chat are having too much fun with your turtles and tortoises and whatnot. So we have problem number 5 in the house, guys. Problem number 5 is done. And if for this problem, we only have y-axis symmetry. There we go. So I'm going to put y-axis in a red box, just like that. How am I doing, guys? Am I doing all right? Is the explanation clear? Are we moving along okay? Are we making progress together, guys? How are we doing? Go ahead and show the chat some love. Put you guys up there in the house. We have problem number 6. And with problem number 6, we have y equals x cubed. Karina says we're doing great. Thank you for the support, Karina. I appreciate that. All right. So we have a cubic function, and we want to test for x-axis symmetry, y-axis symmetry, and symmetry about the origin. How to go about doing this? Well, for starters, since we were already starting out with the y-axis first, let's go ahead and do that. Let's go ahead and keep that trend going. We would need to replace all the x's with negative x in order to test for y-axis symmetry. And so, rewriting this problem as y equals to the opposite of x cubed, simplifying this, you'll end up with y equals negative x cubed. Is this exactly what we started out with? No, it is not. All right. So Treasure Ghost says y-axis symmetry, I think. But once it's simplified, though, Treasure Ghost, TG, if you look at the original equation, this is the opposite of x cubed, whereas we started out with a positive x cubed. Since they're not identical, we can't say that we have y-axis symmetry. However, let's continue on with the x-axis test for symmetry. So testing for symmetry about the x-axis, we would be replacing the y value with negative y. This is set equal to x cubed, and then when you attempt to simplify this by solving for y, for instance, you could divide both sides or multiply both sides by negative 1. You'll end up with y equals negative x cubed. The question is this identical to the original problem? No, it's not. So therefore, this definitely is not symmetric about the x-axis. All right. Now let's go ahead and see about the test for symmetry about the origin. How do we do this, guys? Do you remember? Well, when you're dealing with the origin, all you have to do is replace all the x's with negative x, replace all the y's with negative y, and then simplify. So in this case, we would be replacing y with negative y. We will be replacing x with negative x, and then we'll simplify this. So on our left side, you have negative y. On the right side, you have negative x cubed. However, if I were to try to simplify this by solving for y, I can multiply or divide both sides by negative 1. And guess what, guys? We end up with y equals x cubed. Isn't this the original equation that we started out with? Exactly. It is. It is, Obina. So that means that because we were able to replace all the y's with negative y, all the x's with negative x's, and then once we simplify, do we end up with the original equation? We do. Because we do, we have symmetry about the origin. And this is why our tests algebraically are so important, because I don't want you guys to rest on your laurels. I don't want you to use assumptions. I don't want you to try to predict the result. I want you to use the test and scientifically find out whether or not the result is what it is. Okay? So it's all about proving your results. So that's why you're going to carry out the test. Treasure Ghost, appreciate you chiming in with us today. You take care. Thank you so much. I'm going to enjoy the rest of the stream, and thank you so much for joining us thus far. All right. Thanks so much, TG. You take care. That's Treasure Ghost, guys. Treasure Ghost is in the house. All right. And you know what? Let's go ahead and Obina has been with me for so long. Let's go ahead and graduate Obina to a moderator. There you go. That's right, Obina. You've been down from the beginning. Go ahead and show you some love. Good stuff. So we have problem number 6 in a can, guys. We tested for the x-axis symmetry, the y-axis symmetry, and we tested for symmetry about the origin and found out that it was only about the origin. There you go. Done and done. That's right. Sandra, it's only been it's just been half an hour so far. Yeah, that's right. So let's go ahead and continue on. Obina's in the house as a moderator now, so therefore we can move forward in good hands. Amen, amen. What's going on, Masa? Good to see you. Good stuff. We have problem number 7, guys. Problem number 7, we have x equals y squared. This is going to be a quadratic equation that we're dealing with. We have a quadratic equation. It's actually a horizontal parabola is what it'll be if you were looking at the graph. However, once again, we're not going to rely on the graph. We're going to test for symmetry algebraically. So let's start out with our y-axis test. Testing for symmetry about the y-axis. The way you do that, guys, is you replace all the x's with negative x and simplify. So this would be rewritten as negative x equals y squared. Well, if we're solving for x, as our original problem is, we would be dividing both sides by negative 1, right? If we divide both sides by negative 1, we'll have x equals to negative y squared. Well, is x equals negative y squared? Is this identical to the original equation? No. It's not identical. Therefore, we do not have symmetry about the y-axis. We don't. It has to be identical to the original equation in order to confirm symmetry about the y-axis. Let's move on then to our test for the x-axis symmetry. For the x-axis symmetry, you're going to do the opposite, okay? Meaning that you're going to replace all the y's with negative y. Okay, and simplify from there. So when I plug in negative y for y and then simplify this, we know that negative y times negative y gives us y squared, right? So x equals y squared is identical to our original equation. Therefore, we can confirm, let's go ahead and just slap a red box around this right now, that we have x-axis symmetry based on our algebraic test for symmetry. There you go. So once again, in order to confirm x-axis symmetry, all you have to do is replace all the y's with negative y and simplify from there. That's exactly what you need to do. Okay? That's how it gets done. That's how it gets done, Sandra. Yeah. Just like that. So, once again, we'll be testing for symmetry about the origin. And how is that done, guys? When we're dealing with the origin and our test for symmetry, you would be replacing the x values with negative x. You'll be replacing the y values with negative y. And simplifying, you're looking for the result of this to be identical to your original equation. If it's not, you do not have symmetry about the origin. If it is, you do have symmetry about the origin. So what happens here? We'll just bring down this negative x. All right. We know that on the right side, negative y squared, in this case, the quantity of negative y squared means negative y times negative y. That'll give you y squared, right? All day long. To solve for x, multiply or divide both sides by -1. Simplifying this gives you x equals negative y squared. Is this result identical to our original equation? No, it is not. Therefore, we only have x-axis symmetry for our equation number 7. Once again, guys, I do not want you guys to assume this. Go ahead and prove it. It doesn't take that long to do that. All right. So unless you're looking at the graph and or you're not that familiar with, or you're familiar with your parent functions and transformations of functions, you definitely want to go ahead and trust your algebraic test. Okay. There you go. And then as you get more and more familiar with the graphs, the functions, the relations, all the above, and you have mastery over that, then maybe you can build up some confidence in identifying whether or not you have symmetry just by looking at the equation. All right. But definitely go ahead and do me a favor and carry out the test to prove the symmetry for y-axis symmetry, x-axis symmetry, and symmetry about the origin. Amen, amen. That, guys, was problem number 7. Okay, let's move it on. And guys, I wanted to remind you guys, thank you so much for chiming in with me. And thank you so much for sharing the stream, your thoughts about Fort Bend Tutoring, giving us feedback constantly. And also just wanted to remind you that you can set up a paid online tutorial today with me, Mr. Witt, or any of our available tutors at Fort Bend Tutoring. FBT is in the house. So check out our website, tutormemath.net, where you can find out more information about paid one-on-one tutorials, because that's when I can become your personal tutor, and I would love to meet you and talk about your mathematics. Amen, amen. Let's keep it going, guys. We have problem number 8 now. Problem number 8. Good stuff. We have y equals the opposite of the absolute value of x minus 4. Y equals the opposite of the absolute value of x minus 4. So what do we do with this? If we're going to be trying to test for symmetry, we're going to be carrying out the exact same steps as the previous problems. And what is that? For the y-axis test, testing for symmetry about the y-axis, we are to replace all of the values of x with negative x and then simplify. All right. So I need to remind you that when you're dealing with absolute value, you're talking about a distance, the distance to 0 more specifically. So the distance to 0 in this case, all right, assuming that x is positive, or even if it wasn't, is going to be, let's say, x units away from 0. Okay. That's exactly what it would be. So the opposite of that value, taking the absolute value of that, is going to give you an identical answer. See, for instance, let's say that x was 3. Well, the distance to 0 from 3 is 3, but let's say you're dealing with the absolute value of -3. Well, -3 is still 3 places away from 0. So that means that when you're simplifying the absolute value here, the absolute value of x is going to be identical to the absolute value of -x. So simplifying this, you can go ahead and remove the negative within the absolute value because that value is identical to the original. Okay, so that being the case, we have x is equivalent to, or rather, y equals to the opposite of the absolute value of x minus 4 is identical to that previous step. So taking the absolute value of -x is identical to taking the absolute value of x itself. So that confirms that this result is identical to the original equation. Therefore, we do have y-axis symmetry as far as this equation and function is concerned. All right. So now we're looking at x-axis symmetry. Let's look at the test for that. If we're looking at x-axis symmetry, what would occur is that you would replace every y with negative y. The x value will leave it alone, and then you can simplify this. Solving for y, we would divide everything by -1. Okay, that'll help us get a positive 1y. And this gives us y equals the absolute value of x plus 4. This result is not identical to your original equation. Therefore, you do not have x-axis symmetry. You don't have it. The result has to be identical to the original equation. You don't got that right now. Okay? So you don't have it. What about the origin? What about symmetry about the origin? As we saw earlier, depending on the relation, you can have multiple symmetry. You can have symmetry about several things at once, depending on the relation. All right. So that's why I say go ahead and carry out the test and confirm which symmetry you have. Obina says you just have the x-axis symmetry in this. Let me go ahead and confirm that, Obina and Sandra and Smarty Pants. Let's see. All right. Because you guys already got the answer, of course, because you're awesome like that. And you're much faster than me because I'm over here running my mouth. So let's see if I can catch up to you. So replacing all of the y's with negative y, replacing all the x's with negative x, and then simplifying this, because if I go ahead and divide each and every term by -1, I want to see if I'll end up with the identical equation that we started out with. So far, excuse me, let me go ahead and show that this would just be identical to the absolute value of x here. All right, because we had a negative divided by a negative is a positive. So that's going to be a positive absolute value of x now. And this is going to be positive 4. So when we get y equals to the absolute value of x plus 4, then you do not have symmetry about the origin because this equation is not identical to the original. All right. So therefore, we only have y-axis symmetry. Corinna, you were correct. There's no need to forgive you. You were correct. You were absolutely right. Okay, so there's no x-axis symmetry. There's no symmetry about the origin. You have only y-axis symmetry for this equation. And that's problem number 8. Done and done, guys. Done and done. Let's move on to problem number 9. There we go. Problem number 9 is in the house. That's what we have, guys. And with problem number 9, we have a linear equation. We have y equals 1/2 x minus 3. So what we'll be doing, instead of looking at the graph, we'll be looking at the equation, solving, using the test algebraically to see and confirm if we have symmetry about the y-axis, the x-axis, and the origin. That's what we're here to do. So carrying out our problems here, our process rather, we have the test for the y-axis. And what do we do here? We replace all the x's with negative x and we simplify. That's what we do. That's what we do. Well, aren't you already doing this? So in simplifying this, you'll have y equals to negative 1/2 x minus 3. Is this result the same as the original equation? Is it? Well, is it? No, it's not. Your eyes are not lying to you this time. We do not have the exact equation as before. So you notice that first term on the right side of the equal sign is the opposite. Well, we need it to be the exact same in order to confirm that we have y-axis symmetry. And we don't. And we don't. So we're going to move on. That's what we're going to do. We're going to move on because we do not have y-axis symmetry. So testing for the x-axis symmetry. What do we need to do? We need to change the sign on the y value and simplify to see if we end up with the original equation. Sandra says none of them. All right, so let's see. If I solve for y by dividing everything by -1, let's see what happens here. We end up simplifying this to find that we have y equals negative 1/2 x plus 3, which is not the original equation. Therefore, we do not have x-axis symmetry. Then, looking at our symmetry for the origin, looking for the test for that, looking at the test for symmetry about the origin, what do we need to do? We need to replace all the y values with negative y. We need to replace all the x's with negative x and simplify this. And we want to see whether or not we'll end up with a result that is identical to the original equation. So we have now, simplifying, we have negative y equals to negative 1/2 x minus 3. If I were to multiply each and every term by negative 1 or divide each and every term by negative 1, simplifying this, we'll have y equals positive 1/2 x plus 3, which is not identical to the original problem. And Obina says he agrees with Sandra correctly. So therefore, we don't have symmetry, whether it be the x-axis, y-axis, or the origin. All right. So because of this, you're going to write the following result. You're going to say none. Yeah. You don't have any symmetry about the y-axis, the x-axis, or the origin. So therefore you don't have any. So you're just going to be none. You don't have any of the symmetry. There you go, smart pants. Done and done. We are done with problem number 9, guys, and moving on to problem number 10, where we have a quadratic equation. We have y equals x squared plus 6x plus 1. We're here to confirm the symmetry for this equation, whether it is symmetric about the y-axis, the x-axis, or the origin. That's what we're here to do. Let's go ahead and get my people back in the house. There they go. Looking good. That's right. So therefore, we are looking at the following, guys. The y-axis test for symmetry. What do we need to do? We need to replace all of the x's with negative x and simplify this. That's what we need to do. Oh, yes. Oh, we're not scared. We're not scared. We have negative x squared, which means negative x times negative x. This gives you x squared. 6 times negative x gives you negative 6x plus 1. We then analyze our results and compare it to the original equation. If these equations are identical, then you have y-axis symmetry. You have y-axis symmetry if they're identical. If they're not, you don't have y-axis symmetry. So is y equals x squared minus 6x plus 1 the original equation? No, it's not. Therefore, you do not have y-axis symmetry. You can't force this thing. No, there's no force in this. It is either it is or it isn't. There's no in between here. Yeah, you can't just make it up. Okay, so then we're looking at the x-axis symmetry here. What's about that test? What about the test for x-axis symmetry? You're supposed to replace all the y's with negative y and then simplify. I mean, that's what you need to do. Okay, that's what you need to do. Sandra says none. Smarter Pants agrees that it's supposed to be none. If I were to divide each and every term by negative 1 at this point, in other words, to solve for y, I would end up with y equals negative x squared minus 6x minus 1. Does this equation match our original equation? No, it does not. It does not. But let's not give up, because we have one more test to prove, and that is the test about the origin. And so for the test about the origin, guys, we're supposed to replace all the y's with negative y. You're supposed to replace all the x's with negative x. And then once you simplify, we're looking to see if this result will be identical to the original problem. Let's see if it is. If we have negative y equals to x squared minus 6x plus 1, and then divide everything by negative 1 or multiply everything by negative 1, okay, you'll end up with y equals negative x squared plus 6x minus 1, which once again is not identical to the original equation. Therefore, this result is none. This equation is not symmetric about the y-axis. It is not symmetric about the x-axis. It is not symmetric about the origin. No, it's not. It's not. And that was problem number 10. That was problem number 10. Remembering, guys, that we have 15 problems to look at. Yes, we do. Yes, we do. Sorry about that. Sorry about that. Hand got in the way. But we have problem number 11. That's what we got. And with problem number 11, we have the absolute value of x plus the absolute value of y equals to 4. What you gonna do when they come for you? Is the question. Let's go ahead and see what we can do with this problem. If we're testing for symmetry about the y-axis, what do you do? See, Sandra says it is symmetric in x, y, and the origin. Check out Sandra with her results. off the bat. All right, Sandra, we see you showing off. Let's see. Let's go ahead and confirm this here since you have your answers at the ready. Well, replacing all the x's with negative x and then simplifying this. What happens? As I told you before, guys, since the absolute value is a distance problem, then the absolute value of negative x is identical to the absolute value of positive x. So we can go ahead and simplify this to say that the absolute value of x is equivalent to the absolute value of negative x, because it is. Because it is. We didn't do a thing to the y variable, and we could just bring down the rest. So we do end up with the original equation after our test is simplified. So we already can confirm that we have y-axis symmetry. All right. Good stuff. So Obina says at first he had thought that he was going to disagree about the origin, but after checking it out, after confirming it, he also agrees that it's going to be symmetric about the x-axis, the y-axis, and the origin. Good stuff, Obina. It's nothing like proving and checking your work out for yourself to confirm a result, sir. Let's go ahead and check out this x-axis symmetry here. What am I supposed to do in this case, guys? I'm supposed to replace all the y's with negative y and then simplify. So what happens here? We bring down that absolute value of x. We know that the absolute value of negative y is identical to the absolute value of y because it's a distance problem. That distance would be the same. And once again, we end up with the exact equation that we started out with. That confirms that we have x-axis symmetry. And now we'll be testing for symmetry about the origin. And when we test for symmetry about the origin, guys, we'll be replacing, once again, if I can get my words together, we'll be replacing all the x's with negative x. We'll be replacing all the y's with negative y. And then we'll be simplifying here. Yeah? Are you ready to do that? Are you ready to simplify is the question. Well, the absolute value of negative x is identical to the absolute value of x. The absolute value of negative y is identical to the absolute value of y. And, of course, 4 is 4. And I like this 4 right here. That was a cute little 4. I think I need to frame that. Okay, this 4 right here, I'm really feeling that 4. It's a nice 4. So because of this, we have an identical equation based on the original. Yeah, they're the same. Therefore, this confirms that we also have symmetry about the origin. Therefore, we have Obina correct. Sandra's correct. Smarty Pants, a.k.a. Karina, is correct in the house. Good stuff, guys. So, problem number 11, we have symmetry for all three. Confirmed. That's right, all, Karina. Every last one of them is confirmed. And notice we were able to confirm this without looking at the graph. And that's the beauty of it all, that you did not have to graph this relation in order to confirm that you have symmetry about the y-axis, the x-axis, and the origin. How good is that? Because if you're like me, I'm not too happy about graphing these things, okay? I'd rather just do it algebraically if I have a choice here. And being as though we are going over this test and its algebraic test and how to apply it, this gives you another tool in your belt to go ahead and apply this when you're asked to find symmetry when it comes to these types of equations. All right, so you just completed problem number 11 correctly. You are a math boss. Exactly. You are a math boss. Obina says that this function is a square. Well, I will tell you this, Obina. If the graph is a square, it is not a function. And the reason why it's not a function is because it would fail the vertical line test. All right. So you would say in that case properly that the relation is a function. See, a relation is a group of ordered pairs, whereas a function is a relation where none of the x values can repeat. So if you have a square as a graph, you'll have some points that share an x value that's the same. Therefore, it is not a function. It's called a relation instead. So that's the difference between relations and functions. So the bottom line is that every function is a relation, but not every relation is a function. Okay? So there you go. Just like every square is a rectangle, but not every rectangle is a square. All right. How you like that? Good stuff. Look at you guys getting more information out of me today, making me work harder for you. All right, well, it's my pleasure. We have problem number 12, guys. We have x squared plus y squared equals 3. What you going to do with this one? All right, Tammy is in the house and says, thanks. You're welcome, Tammy. It's my pleasure. Thank you so much for chiming in today. I appreciate your presence here. All right, it warms my heart. There you go. So we're looking at problem number 12. And we have x squared plus y squared equals 3. We're going to be checking out our test for symmetry here. And with these tests, we will be starting out with the y-axis test. That's right. And how do you confirm symmetry about the y-axis? Well, all you have to do is replace all the x's with negative x and simplify this. Well, notice that I'm replacing my x's with negative x here. I'm going to simplify this knowing that negative x times negative x is x squared. I can bring the rest of the equation down and notice that it is identical. Our result here, once simplified, is identical to the original equation, which means we definitely have y-axis symmetry. So anytime you're trying to confirm y-axis symmetry in an equation, all you have to do is replace all the x's with negative x and simplify that. And once you have it simplified, you can confirm that if your result is identical to the original, you have y-axis symmetry. We already have Karina and Sandra talking about which of the tests are passing for them. Let's go ahead and see if we can catch up to them, guys. Let's go ahead and check out our x-axis symmetry now. For x-axis symmetry, what do? You replace all of the y's with negative y. And then you simplify the equation. So I'll be bringing down my x squared, knowing that negative y times negative y is y squared. You'll have positive y squared as a result. What's going on, Angry Hermit? Good to see you. Good to see you, Angry Hermit. Today, we're discussing symmetry and test for symmetry algebraically. This is a topic that you can do in college algebra, algebra 2, pre-calculus, calculus, trigonometry. All of the above. That's right. And that's right. We had Obina graduate to moderator today. So Obina is saying, what's going on, Anchor Hermit, fellow moderator? That's right. Anchor Hermit is an OG moderator, Obina. That's right. Angry Hermit plays no games. So here, what happens with the x-axis symmetry, guys? Notice that our result here is identical to the original. So this confirms that we also have x-axis symmetry. We also have x-axis symmetry in this result right here. Amen, amen. So 2 of the 3 tests have already been proven to pass. Let's see about the test for symmetry about the origin. What happens here, guys, is that you need to replace all the x's with negative x for this test. You replace all the y's with negative y for this test, and you simplify this. Well, simplifying, you get negative x squared, which is negative x times negative x. That gives you x squared. Negative y times negative y is going to give you y squared. And once again, we end up with the exact equation that we started out with. And that being the case, Angry Hermit, no, OG doesn't stand for orange juice. What's wrong with you? That would have been OJ. And I just took a sip of orange juice just for that. Okay. So here we have a red box coming for our origin test that passed. So our problem number 12, the equation x squared plus y squared equals 3, which is a circle, by the way, guys. This passes all 3 tests just as we proved with the circle graph that we had originally, because at the beginning of the video here, because it is based about the origin. Amen, amen. That's right, Smarty Pants. They are all passing in this equation, and let us move on to the next equation. What are you going to do with this one? You have x equals y squared plus 3. X equals y squared plus 3. And we want to test for symmetry about the y-axis, the x-axis, and, amen, amen, Sandra, right? And the origin. That's what we're here to do. Okay, so let's try with this y-axis symmetry. Remember, the test for the y-axis symmetry is actually meaning that you're going to, is carried out by replacing all the x's with negative x and then simplifying this. Okay, so if I were to divide each and every term by -1, in other words, solve for x as it is in the original equation, we would end up with x equals -y squared minus 3. This result is not the same as our original equation. Therefore, we do not have y-axis symmetry. So the first test failed. However, we're going to try the x-axis test now. And when we're testing for symmetry about the x-axis, we're going to replace all the y's with -y and then simplify from there. So simplifying, -y times -y gives you y squared. And we end up with the original equation, right? Yeah. So therefore we can confirm, just as Smarty Pants did, we can confirm that our x-axis, we do have symmetry about it. Yeah, we sure do. We have symmetry about the x-axis. Then if we take a look at our symmetry about the origin, so let's go ahead and spell this out. For our test for symmetry about the origin, Obina says x-axis only. All right, let's see about that. We are going to be replacing all the x's with -x. We'll be replacing all the y's with -y and then simplifying this. Okay, so we have -x equals y squared plus 3. If we divide each and every term by -1 to end up with a positive x, you'll have x equals -y squared minus 3. This is not the exact same equation as our original, guys. So therefore, just as Obina and Smarty Pants Karina has pointed out, we have symmetry only about the x-axis. We only have symmetry about the x-axis. That's it. Yeah, just like that. That's problem number 13, guys. That is problem number 13. Let us move on to problem number 14 as we're looking at the equation of an ellipse. That's right. Looking at the equation of an ellipse in this problem right here. Amen, amen. Yeah, that's what we got. So let's check out problem number 14. What happens here? If we have x squared divided by 9 plus y squared divided by 16 equals 1, what occurs? In this problem, we're going to say that we have the following problem here. We have the y-axis test coming up, and we're to be replacing all the x's with -x. What happens here? You'll have -x squared divided by 9 plus y squared divided by 16, and this equals to 1. If I were to simplify this, we know in the numerator that we have -x times -x is x squared. Therefore, you would have x squared divided by 9 plus y squared divided by 16 equals to 1. And so we pass the y-axis test. We already have Sandra saying all. We already have Obina saying all. We already have Smarty Pants Karina saying all. That's right. And Sandra says that Obina beat Sandra just by a second. Good stuff, guys. We confirmed that we have y-axis symmetry here. That's exactly what we confirmed. And now what we'll be doing is we'll be testing for the x-axis symmetry to catch up with the chat. See, the chat is on fire right now, guys. Can y'all catch up with that chat? All right. They are fast with it. So this test here for the x-axis symmetry is where you're going to replace all the y values with -y. So we're going to bring down here this x squared divided by 9 plus the quantity of -y squared divided by 16. Let me get my lie right. There we go. And then we'll simplify this. So simplifying this equation, you'll end up with x squared divided by 9 plus y squared divided by 16, and this equals to 1. Well, this equation is identical to the original equation. Therefore, we can confirm that we have x-axis symmetry as well as y-axis symmetry. And now when we test for the origin, remember the test for the origin involves us replacing all the x's with -x and all the y's with -y. So that looks like this. We'll have -x squared divided by 9. We'll have negative y squared divided by 16, and this equals to 1. So when we simplify this, we're able to end up with the result x squared divided by 9 plus y squared divided by 16. And this equals to 1. This equation is identical to the original equation. Therefore, my chat is correct. You guys are off the chain correct, because Sandra's right, Karina's correct, Obina's correct, and you guys are going off with the correct answers. I'm so proud of you guys. And many of you are just seeing this concept for the first time and already are knocking it out the box. You see what I was talking about at the beginning, Karina? You see how you can learn a new concept and become comfortable with it and start mastering it with Fort Tutoring. And therefore, when you get back to class and these concepts come up, you'll already be familiar with them. And you can share your knowledge with your classmates. And that is very, very powerful. All right. Good stuff. Okay. Let's take a look at our last problem of the video. This is a trigonometric function that you guys may or may not be familiar with. It is the cosine function. And in our previous video where we discussed cosine functions with being even or odd, we learned a few rules about the cosine function. So I'm referring to the even and odd function test that we were discussing last week, guys. All right. So if you didn't see that video, go ahead and check it out to expand your repertoire. All right. Expand your knowledge in academics and mathematics. So let's start with the y-axis test. The y-axis test says that you would be replacing all the x's with negative x. Well, the cosine function, guys, is an even function, which means that by plugging in negative x into the original equation, it is equivalent to cosine of x. Because the cosine function is an even function, plugging in negative x for x and simplifying it gives you the original equation. So therefore, this function is symmetric to the y-axis. Sandra, you are correct. Let's go ahead and check out the x-axis test. For the x-axis, you'll be replacing all the y's with negative y and then simplifying. Well, dividing both sides by negative 1 to solve for y, you'll have y equals the opposite of cosine of x. Well, guys, this is not identical to the original problem. So therefore, this function, this graph, is not symmetric with the y-axis, with the x-axis. It is not symmetric to or about the x-axis. Thus far, it is only symmetric about the y-axis. All right, Obina says same, confirming that Sandra's answer is where he wants to be. All right, is where he's trying to go with it. Let's check out. Smarty Pants says y-axis only. Well, let's see what happens when we go with the origin test. The test for the origin, guys, has the following. We would be replacing all the y's with negative y. We would be replacing all the x's with negative x. Okay? So let's see what that looks like. We know that we would be bringing down the negative y, and I already told you that cosine of negative x is identical to cosine of x. So in order to solve for y here, all you'll need to do is divide or multiply both sides by negative 1. And then simplifying this, you'll get y equals to negative cosine of x, which is not identical to the original equation, guys. Therefore, your only line of symmetry here is going to be with the y-axis. So this function is only symmetric to the y-axis. Done and done. Well, I want to give a shout out to everybody that hung out with us. Make sure that you are liking the video, sharing the video, commenting on the video. And we appreciate Obina stopping by today. We appreciate Smarty Pants, a.k.a. Karina, stopping by today. We appreciate Angry Hermit in the house. Tammy was in the house. We also appreciate, let's see who else. Mike Jackson was in the house earlier today. Darian Jones was in the house earlier today. Yes, he was. Yes, he was. Treasure Ghost was in the house. Sandra's in the house, of course. That's right. And we appreciate everybody that is watching right now. We also appreciate BGS It More with the donation. That's right. So once again, if you want to donate to Fort Bend Tutoring, if you're in the middle of our live chats, then you can check out that dollar donation there, that dollar sign at the bottom, to do a super chat donation. We really appreciate that. Or you can find a link for the donation link in the description box. Amen, amen. And help us out here so that we can help out more people with your assistance. That's right. And do not forget, guys, go ahead and subscribe to Fort Bend Tutoring, where we bring you free math tutorials on our YouTube channel. And lately, we've been bringing you weekly videos and live streams. That's right. Where, of course, we got my people in the house right here that is in the chat sharing the love. All right. So there we go. I appreciate you guys spending time with me. And Jefferson is in the house. Thank you so much for stopping by, Jefferson. I appreciate you being here with me. And as always, please rate, comment, and subscribe. Peace.
Thanks for watching. We appreciate you hanging out with Fort Bend Tutoring. Like the video, comment, and subscribe. Hit up our website, tutoringmath.net, and set up a private tutorial with me and FBT.